In this video, I'll show you the inverse Euler formulas and illustrate their use in a problem. If Euler gives us the complex exponential in terms of sines and cosines, then inverse Euler gives us sines and cosines in terms of complex exponentials. Here are the formulas. Inverse Euler. Well, cosine of theta in terms of complex exponentials is e to the j theta plus e to the minus j theta over 2. Sine of theta is similar. Sine of theta equals e to the j theta. Now subtract minus e to the minus j theta. And we don't divide by 2, we divide by 2j. The proof is rather easy. Before starting the proof, let's note one thing. E to the minus j theta equals cosine of theta minus j sine theta. This is because cosine of minus theta is cosine of theta, and sine of minus theta is minus the sine of theta. Now we can start the proof proper. Looking at the formula for cosine theta, it suggests writing out this sum, e to the j theta plus e to the minus j theta. We use Euler's formula to write that as cosine theta plus j sine theta for the first term, and plus cosine theta minus j sine theta for the second term. This follows from our note above. This sum is quite easy. The cosines add. We have 2 cosine theta. The sines cancel. All we have to note is that we take this 2 and divide it to the other side, and we have the inverse Euler formula for cosine. The proof for sine is nearly identical. I'll do it a little quicker with fewer words. I start with e to the j theta minus e to the minus j theta. I write it out. I have the same 2 terms. But they have a minus sign between them. Now when I subtract, the cosine cancels, and I end up with 2j sine of theta. Once again, if I divide by this factor of 2j out front, I end up with my formula for sine. In the next slide, we'll illustrate the use of these formulas in a simple problem. Now we'll illustrate the use of inverse Euler with the following problem. Find the integral of sine of at cosine of bt dt. We replace sine and cosine by their complex exponential formulas. Sine becomes e to the j at minus e to the minus j at, all divided by 2j. Cosine becomes e to the j bt plus e to the minus j bt, all divided by 2, and we multiply by dt. We multiply this out, we'll get 4 terms. We'll try to do it in a good order. We have first e to the j at times e to the j bt. That gives e to the j a plus b t. Next, I'll do these last 2 terms, e to the minus j at times e to the minus j bt, and that gets minus e to the minus j a plus b t. Next terms are, again, the first term, e to the j at times e to the minus j bt, so we have plus e to the j times a minus b t. Last term, minus e to the minus j at times e to the j bt. That works out to minus e, and I'll put the minus out front, j of a minus b t. We have to put the whole thing over 2 times 2j dt. If you didn't follow my algebra, just write it out yourself. It's easy. I'm going to take this 1/2 right there and put it in front of my integral. Now, this term right here is just our formula for sine of a plus bt. And this term here is just the formula for sine of a minus bt dt. These are easy integrals. I end up with minus 1/2 cosine of a plus b t over a plus b plus the cosine of a minus b t all divided by a minus b. To finish off, we'll note that in the process we actually learned a nice trig identity. We learned that sine of a times cosine of b, here I'll just set t equal to be 1, equals 1/2 sine of a plus b plus sine of a minus b. That in itself is a useful identity. Here we used inverse Euler to help us compute an integral, but you can use these formulas anytime it's easier to work with exponentials than sines and cosines. They're important formulas. Again, I encourage you to remember them.